Look at the surface of Enceladus. By all accounts, this small moon orbiting Saturn should be a geologically dead rock, frozen completely solid for billions of years. But it is highly active. The moon is firing 80 gallons of water per second straight into space from deep fractures at its south pole. If we look at this cross-section of the moon, you can see why. Hidden beneath that icy crust is a churning liquid ocean, roughly 6 miles deep, almost as deep as Earth's Mariana Trench. That water stays liquid so far from the sun because of Saturn's immense gravity. As Enceladus follows its oval-shaped orbit, it gets constantly stretched and squeezed, creating a massive amount of internal friction and tidal heating. This constant geological grinding takes a frozen wasteland and turns it into a massive, naturally functioning astrobiological reactor. When NASA's Cassini probe flew directly through those erupting plumes at 19,000 miles per hour, it physically tasted the water. It found complex organic macromolecules, intricate carbon rings containing hundreds of atoms. These are the exact heavy-duty chemical structures required to assemble amino acids and build living cells. This raises a question. If a deep water ocean with a steady heat source is churning out the perfect chemical recipe for biology, why didn't the probe detect the alien cells themselves? It comes down to a strict engineering limitation. Cassini was built to be a weather and geology satellite. Its instruments were designed to weigh molecules and measure magnetic fields. It completely lacked the microscopic resolution or the specific technology needed to sequence a strand of DNA or image a living cell. Cassini tracked the chemical signatures of a habitable world, but it lacked the specific tools to identify the biology itself. We found the smoke while carrying sensors that weren't tuned for the fire. Take a look at this standard model. For decades, the scientific consensus held that our sun's solar wind pushes outward to create the heliosphere, a perfect, symmetrical, protective bubble shielding our solar system from deep space. But when the Voyager 1 spacecraft, a piece of 1970s engineering running on a fraction of the memory of a modern smartphone, finally reached this boundary in 2012, that pristine mathematical model collapsed. Watch what happens when we adjust the shape to match Voyager's actual data. The bubble is violently squashed at the front and dragged out into a long, turbulent tail at the back, deformed like a teardrop by the intense headwind of the interstellar medium. Beyond the distorted shape, Voyager proved our mathematical models were physically disconnected from reality. The spacecraft traveled over 2 billion miles past the point where theoretical physics claimed the solar system ended. If our most trusted calculations are off by billions of miles, right in our own cosmic backyard, our grasp on the universe's rules is incredibly fragile. Voyager detected a second major anomaly at this border, a highly organized structure scientists now call the magnetic highway, piercing straight through the edge of the solar system. In this region, the sun's magnetic field aligns directly with the magnetic field of the galaxy. It acts as an open channel, allowing solar particles to shoot straight out, while lethal, high-energy galactic cosmic rays shoot straight in. Absolutely zero existing cosmological models predicted that a structure like this would bridge the gap between our solar system and the interstellar void. If the physical laws we rely on are already breaking down at the border of our own star, we have to ask what happens when we look into the deep past. The James Webb Space Telescope was built to look past those boundaries. By capturing ancient, stretched infrared light, it can peer back 13.5 billion years, capturing light emitted shortly after the universe formed. When astronomers pointed it at the early universe, they found targets like MOMS 14 and the gargantuan cluster XLSSC 122. These are galaxies existing within the first few 100 million years of cosmic history, an era previously thought to be a featureless fog of hot gas. According to standard cosmology, gravity is a patient engine. It takes billions of years to slowly pull raw gas and dust into massive structures. Yet these distant galaxies are already ancient, hyper-evolved, and fully formed. They are so dense and tightly packed that their immense gravity is literally warping the fabric of spacetime, bending the light of anything positioned behind them. Finding a massive, hyper-evolved galaxy within the universe's first 300 million years forces us to reevaluate how matter actually organizes itself. But the final pattern astronomers are uncovering is even stranger. They are finding that the majority of these ancient, distant galaxies are all mysteriously rotating in the exact same direction. To understand why that breaks the Big Bang Theory, look at these two data maps. In a universe born from a totally random, chaotic explosion, the visualization on the left should be true. Galactic spin directions should be split 50-50. Instead, the visualization on the right shows them locked in a single synchronized flow. To explain this uniform spin and the missing time required to build ancient galaxies, some physicists are turning to a radical idea known as the Big Bounce. This theory suggests the Big Bang wasn't an explosion out of empty space. Instead, it was the moment matter collapsed into a superdense singularity, generated a repulsive force through physical twisting, and violently rebounded outward. This rebound suggests the Big Bang was the moment matter collapsed into a singularity and birthed a new expansion. This links our origins to the physics of black holes, leading to the theory that we are currently living within the event horizon of a black hole formed in a larger parent universe. If this model is correct, every black hole we observe in our night sky might be the starting point for another universe, invisible to us, but containing its own cosmic history. We just need to build the right lens to see it.